All right. Okay, welcome back to the second lecture of the deep learning course. I hope you had a good lunch and are not too sleepy. I think I see here and there some sleepy eyes, but I try to get you back. And in between, please check your runs, especially if you have done some neural network ones with the hidden layers. Now is the time to look, and hopefully you will observe from the first lecture that the accuracy was increasing. So who can see the output of the job increasing the accuracy? There's two hidden layers. Okay, right? So that's interesting, moving, adding more layers. Interesting enough, in the break we just had the discussion, if you add more and more layers, you add more and more weights, and this should ring alarm bells because you add lots of weights. And weights needs to be learned. And with this, you have an outbalance of the problem versus basically the weights you have to learn. In other words, it's a nice reflection of overfitting. We had also in the basic machine learning case, we have by far too much weights to be very good in a good accuracy learned. Hence, the accuracy will drop. So it's something also, if you want, you can try out. Add more hidden layers, reduce the number of neurons, add the number of neurons as you like. As long as you stay on the non-GPUs, you can use the system very freely. For the GPU ones now in Leuven, we have to be a bit more careful. However, let us come back to the main part of the lecture here, which is really now convolutional neural networks. So who has used convolutional neural networks before? Okay, that's not many. For those of you, that will be a bit boring maybe, because I go now through all the different types of layers. So tomorrow would be more interesting when we do some regularization, validation experiences. But let's go and understand where and what exactly are now these convolutional neural networks. And what are the tools basically behind the scene. We will start a little bit with the basic principles, but I would like to bring you the basic principle also in light of a practical application that you already know, right? So we will stay with MNIST, and we'll also submit then ourselves a convolutional neural network as part of this lecture. Then in the next lecture, toward the end of the day, we go more sophisticated using a remote sensing dataset, which then takes actually all night or several hours to compute. However, here we will stick basically also to the GENT system, right? So this is still a, let's say, manageable system. However, you could, of course, also increase it significantly in speed if you use GPUs, but here stay on the GENT system still. Right, so we will shortly looking a little bit on the overfitting that I just discussed with the neural network and the weight problem, which was a nice, let's say, link to this, and how we can a little bit solve it with convolutional neural network. We cannot perfectly discuss it today because we need some material of tomorrow, the regularizers, weight drop, weight decay, and these things, and we cannot put everything in one lecture, right? So bear with me, these will come. And then we will have some advanced application examples where convolutional neural networks are really successfully used with us and by others. Then, of course, a little bit we left lecture one on a sad note in a sense. We didn't really understood how it works under the scene, right? We use keras, add, model, dense, have, you know, a very nice, fully connected hidden layer. But how is the execution done? How is backpropagation done? The chain rule, if you remember, of taking the derivatives. How is that executed on the nodes in parallel and so forth? We have to a little bit look into this for the low-level deep learning libraries that exist. And of course, in our example, we use the back-end TensorFlow, right? In a similar manner, keras can be also used with Theano. And basically what you see as a user is not very much changes. You have to specify that here and there in the job script and aspects. But still, this is a takeaway message. You can use this Theano. You can use also keras with, for instance, Theano and TensorFlow. However, we pick TensorFlow because in many cases it's the most known one, and of course the one that we will basically use here. Toward the end, we will review a little bit of this backpropagation and chain rule just to really understand how the optimization takes place, and then also learn a little bit what is a tensor and so forth. So at the end, still we should look at some of our runs and hopefully see that the convolutional neural network will help our classification problem. And we set the marks very high, right? When you think about the hidden neural network is already, you know, kind of very high in the 90s percentage. How in the world are we going to top that? There are two elements in that. The first one might be speed up. We can maybe faster get this accuracy Or we can even beat that of saying we get even more accuracy, right? Which is still a question mark. We will see how that materializes during the course of the lecture. So let's start very simple, again, with what we already know, our tool set, right? By now you can actually probably read that diagram now out loud when you wake up at night, but it's really the blueprint for classification. So all we change again from our mechanisms is really not much, right? You think about, you still have samples, you have basically labels in the samples. Here and there we will change the error measure a bit more sophisticated, but in a sense what we exchange is only the learning algorithm and the hypothesis set. So in terms of just using now, let's say an artificial neural network with 1 hidden layer, 2 hidden layer, or 3, whatever, we use now convolutional neural networks. And what the algorithm is that actually goes with it is interesting, because that's also what you already in principle know. It's backpropagation. It's of course here and there modified for a more sophisticated structure, like for instance 3D tensors we will talk about, right, in these aspects. So it's a little bit more sophisticated, but the key principle that you have seen in forward propagating, you know, the kind of signal and then taking the error measure backwards still remains. So let's have our example that we already know, basically. That is a character recognition. And there, of course, now, and this is a challenge of deep learning we will come back to in the next lecture, lots of different convolutional neural networks that could tackle that problem. How to find the one that works, right? This is a key question, which basically now differentiates the feature engineering aspects to this feature learning aspect we discussed. Previously, we did feature engineering, manual work on the data, give it to the SVM. We knew almost exactly how the SVM will operate. We have a Riedel basis function kernel. We basically know exactly how it works with cross-validation, a couple of parameters. That's what we've done last week. Now, the work on feature engineering, apparently we don't have to be done now anymore, but the question still arises how you create now something like this, right? You see here kind of a playing field, where I would like to start from the back, interestingly enough, because the back is something what you already know. In the end, we want to do something like a classification, right? That means we would have digits as guiding output from 0 to 9, something we already know, right? And then the fully connected aspect, what could that be if you think about it? Any idea? It looks very similar to something you know. Right? In the end, it's almost an artificial neural network we have used before. There's a softmax function at the end, deriving the probabilities to which class you belong to, and it kind of usually flattens the signal here of saying it's a long, long input vector in a fully connected network doing the classification. So you see, basically the key idea of the neural networks are inherently in the deep learning, especially in the end of the game, in the end of the part. That's interesting. Now what you see in the beginning is then this aspect what I described as automated feature learning. So now is the interesting aspect that where normally we would say, okay, it depends a little bit what the context is, the spatial properties, we massage the data, we work on the data manually, we prepare it, have multiple dimensions, do principal component analysis. I extra speak in this way because people that work in the field know it's 80% of the work or 70% of the work to prepare the data, right? So in this sense, all of this is in this red box and now, interestingly enough, automated. Admittedly, it's automated for pictures, for images, and so on, right? And the more sophisticated you go in identifying, for instance, single pixels instead of to whole themes, that's something we will talk about. Of course, you have to structure your network differently and will become more and more complex. Hence, you also have to think a little bit about what you put in front. So what we're going to do though in part of this lecture is we talk about the different layer types. You see here kind of the key difference to the later. This is very simple, just neurons densely connected, we know already. But here are certain properties like feature maps and convolutions. We do pooling and subsampling. We will go layer by layer to understand what that means in the context of the MNIST application example. However, we kind of think, even if we improve the classifier, these are good examples of saying, again, machine learning, well, 100% would be very hard to do. right? So if you think about, maybe I have a poll for the audience, what is this about? Any idea? What could that be? A 2, okay. Another opinion? 7. Yeah, so some people think, how in the world can you come to a 2? Right, so you see, I think you agree with me that these ones would be very hard to classify, right? These ones are a completely different story, but there will be always some parts in the data which is almost not really learnable. Hence, we will probably go to a model which is perhaps going towards 100%, but not having 100%. Again, the takeaway message from machine learning. So the key aspect why that works are so-called local receptive fields where it all begins. And interestingly enough, so we now start from the beginning. While we know that in the back there will be a neural network and doing the softmax, from the beginning you basically think about it's very similar like our visual cortex. You basically see lots of different signals and they are filtered out. And actually our brain is also aligned in different layers in that context. So it would take another biology lecture to come there, but it's not required. Just bear with me and think about what we just do is having lots of input neurons that we already know. That is the pixel image we already used, right? We reshaped it to one vector in the neural network in order to kind of flatten it out. It's something what we also have to do here in convolutional neural networks later. But what we just do is basically we think about local and spatial properties of this, right? So this is now a key thing. Firstly, we focus on images and think about when you recognize a cat or recognize a dog, whatever, the spatial pixels around it, right? If you now think this is a pixel by pixel image, the local part of it would be very important for the classifier to understand. And those of you who have been in the machine learning lecture last week know that from the mathematical morphology we did with the surrounding neighbor pixels. It increased the classification of remote sensing. It will also increase the classification in any other image that has this property. And the most of them have this property, even the remote sensing ones, which are usually pixel-based, right? But here you have, let's say, characters. So the neighborhood neurons will significantly give you guidance. Is it a 0? Is it a 1? Is it a 9? And what you basically do now, you kind of slide over that. It's like your visual cortex looking basically to some certain part that we call local connectivity, which is a configuration parameter now. So this is the first aspect of this convolution. No one tells you how big it should be, right? So this makes right of the complexity, why you spend 1 month of massaging and looking how the CNN really is working and what are the parameters. You just have not number of neurons, right? This is the only part basically that you have in the neural network that we had. Now we basically have a much more complicated problem in just the first layer. So we have this part, and what we do with it, let's say we assume now we have a 5 by 5 spatial property, and this depends on the data. In some cases you would go more, in some you go less. However, take into account, of course, the smaller you do, the more parts of the feature map you generate, right? So here we basically see that this local connectivity, all of them are reduced to 1, right? In this sense, we significantly reduce. But think about that we slide now over that, like our visual cortex is kind of rudder over what we see. We have the first hidden layer, gets the input neurons and slides just over it 1 by 1. So with this we get redundancy, right? Everybody sees that these pixels, you know, for instance, are used twice to create a signal in the first layer. And it goes on and on and on. And this is one of the first aspects of this convolutional part. Now, of course, this parameter automatically comes by picking here, for instance, 5 by 5, and then basically connecting now to the next layer, not in the way how we used to be, was fully connected, right? So now this is basically a connection which is just to this specific neuron in this particular field in the next layer, which is our first hidden layer. So it's already a complete different property if you think about from the others that we had before, right? We had a fully neuron to every other neuron in the hidden layer. Right? That's clear, everyone? Otherwise, of course, here and there you can also ask questions. But it also goes clear if you go the example through, and then if you do the practicals, of course, it becomes eminent. Now, when we do this now, let's consider back what we did in the neural networks. Right? One of the key problems in overfitting that we also discuss tomorrow morning with regularization and so forth is the number of weights to learn. Right? So consider just that you would have, let's say, the input that we discussed before, and we would have 15 neurons in the part of the hidden layer, and we multiply that, then we get already these number of weights to learn. And this is already much more than basically you would have in kind of the different feature maps that we learn, because we just have a local connectivity already. Okay, it goes sliding over it. But there's an interesting property with weight sharing. That means the weight that you learn are shared across each of the feature maps. Now that's just a little bit more in a visual exploitation, but if you add more and more hidden layers, and this would be the problem why the accuracy would then mostly go down, because you lose the bound for those that have been last time there. Right? You have much more training parameters to learn compared to the capacity of the machinery. So and the data that you have, right? It's a very simple data set in MNIST. There could be more sophisticated data where you can use it. So this is something where overfitting will take place if the more layers you add. Now, how we target this in deep learning when we say deep means add a layer, add a layer, add a layer. Right? In deep learning, you would now face a problem we are significantly running into overfitting. Doesn't make sense. So the solution to this is twofold. Firstly, we will downsample significantly here and there. And secondly, we use weight sharing across the different feature maps. So when you now go to your own RNN doc, basically the two hidden layers that you have, you basically can see the parameters there, right? Which is a key property I want to show now in our exercises, just because when we later run the CNN models, to get this into perspective, and when you do your exercises, perhaps I'll be able to show you at home. The nice thing is here you can print out your layers, and some of you have probably seen that already. I'll just take here now one example I have. Just go to your output. I had one prepared here. Scrolling. No. Then did it.
Increase the font a bit.
Ah, okay, yes. The back cannot see so much, so I can just inform. You always have to tell me that. Yeah. Better visible. Are we working on a break on something else? So I have to get back to the connection. But largely, every one of you could do that by just going into the output of the hidden layer job, for instance, and looking on this part at the top. You see nothing else basically than our visual expression that we already know and that we programmed in Keras, right? So everybody got that output, right? From the hidden neuron, okay? Right. If not, talk to our people here and there that can help you to get the runs going. Right? But here you see nothing else. Our dense layer, dense layer, dense layer. The first is really just the input. But you see also at the end it goes down. And why it goes down? We have the softmax layer, right? That is also something to explore. In the end, there are less weights towards the output neuron. Has someone an idea why? Why there are so little params? And here so high parameters, when you think of weights. Yeah?
Well, you want to classify, right? So that's why you have 10?
Exactly. Very good. Now, if you think about the visual expression, we go down to 10 neurons, which are giving our signal out of saying 0, 1, 2, 9, which is our probability basically coming out of the softmax. So in a sense, the weights and the parameters are significantly going down towards the end. Here we had 128 neurons in the hidden layer. All of them are dense, fully connected, to the next layer. Right? This means the high number of parameters. Then the activation is the function that we put through, the ReLU, if you remember the last time. So that's of course something which then is applied to the signal coming through. But if you increase now more and more of these layers, these params will significantly go up and up and up and up in the hidden and so forth. So you see already from the total number of parameters that we kind of, learn and have to work with, trainable, these are 118,000 already. So it quickly goes up with the number of hidden units you add. Right? So one idea would, of course, reduce the number of neurons. So 128 is maybe a little bit excessive for such a small MNIST. So if you have time now, resubmit the neural network hidden, basically, shortly, and reduce the number of neurons by half. Right? And see what the accuracy is. Just take a minute for that. Would be an interesting learning experience. Remember, we're not on the GPUs yet, just CPUs. And we want to explore a little bit how, with different layers, the accuracy will change. I demonstrate a bit what you have to do for it, but please go ahead for those who knows how you should do it. If you remember, we had this magic Python script with the hidden layers here. And there was this one interesting parameter number hidden, which is nothing else than the hidden neurons that you have. Right? And if you now reduce that significantly, and we had a very high accuracy, so maybe there's no point in doing that. Maybe we just can save some computing time doing it. Right? Which is another factor in all what we do. Think about that computing time usually is very, very costly in a sense, right? Scientists and engineers may not pay something, but it is limited. A supercomputer is often used by others. So reducing also maybe the time, if it is possible, of learning all of this is a key thing. And you have seen the parameters fully connected to each of the neurons. So by reducing by factor of 2 per hidden layer, we can see that the number of weights to be learned will be significantly reducing as well. However, if you reduce it too much, in the hidden layers, of saying I just do 4 neurons in the hidden layer just to save computational time, is something also what you can do or at home after the tutorial, but you will significantly see that the capacity of the machine, of the neural network, will not catch the data. In other words, very much bad accuracy that will significantly decrease. Hence, a factor for validation and aspects we have to discuss tomorrow, model selection. How do you determine the number of neurons? It's not an easy topic, right? It's model selection, validation. Those that have been in the lecture last week knew. Also for SVMs, it took grid search, cross-validation runs to get to the best parameters. However, you see more and more in deep learning and neural networks, it's huge. Very high number of parameters. So a real typical grid search, we did this together here for the RBF kernel and the SVM, if you remember at the end of the lecture, for instance. And this was just two-dimensional. Right now, think about what we have to do now, number of neurons, number of layers. We already discussed the convolutional aspect of saying how much local receptive field this should be, how big exactly. So you have, also lots of steering parameters, more and more. It's not an easy topic of creating a CNN. Right, so by having changed to factor 64, you can queue up as usual using the hidden neural network job script, but remember also to have again your reservation included. Everybody could do that. Yeah, has changed the Python script to 64. Who has not done that? Who has a problem with changing to 64 and submitting to the hidden neural network in the reservation? No one? Everything works. Okay, going once. Twice. Okay, good. So then we can go more deeper using the time now while the computing is doing the job in understanding a bit more about convolutional networks. We have to break here in between always to use the time really to get the computing going, right? It's a little bit less interactive with the batch processing, that's why back and forth, but it's the best way of keeping you also short to practical learning. Right, so that's where we left. We said something like, okay, we have the input neurons 28 by 28, and now it's an interesting thing is that, we said how it will be connected. We said like, where we did, for instance, local receptor field up to 5, we can kind of bring that to something which is 24, 24, largely overlapping. Something we can still, let's say, tune also. We can say how big the local receptor field is. This is just an example. But the interesting thing is now what we do, we share the weights between them, right? And with this now, thinking about the full connected that you learn, all are different. All weights are different. You share the weights. And this has a nice property of saying wherever we detect a feature, right, it will be not necessarily very much depending on where we find the feature. Is it up here or up there? So we get a kind of location transparency with this mechanism. Plus, we do also the feature maps. I just finished the feature maps and I come back, right? Because now the question arises, when you don't do this with this signal, how do you get into other signals or other features to speak, right? One signal could carry different features. How does a 0 look like? How does an 8 look like? And so forth. So what you then can do is basically you create different feature maps from that. Also a kind of aspect you can steer depending on your tensor size. The tensor is not obvious, we will come to this later. But basically you can see when you come back to the original picture here, go from there to different types of feature maps that you have here in between. By just one convolution, creating, for instance, each of one. So you're connecting basically every of these kind of internal layers within one layer that are all 24 by 24 actually. With these feature maps, you can come down and create then different features. So examples of that could be different ones. So one, for instance, the grayscale here could be one feature. If you have images, one idea could be to have 3 feature maps for RGB. Right? And with this, you're kind of flexible of how many really of these feature maps you do. And of course, it should relate a little bit to what you expect in terms of the dimension. So we'll see in remote sensing, we have kind of, for instance, 200 spectrum channels. Then we probably think about dimensions of creating more features around these lines. So it's a little bit, let's say, abstract notion, feature maps, but they will carry then the essence of how you learn and how you detect a feature. However, we come back to this again and again. Basically, we'll reuse it then in the practicals and it's get a little bit more clear. There was a question in between somewhere. Yeah.
Yes, so I'm not sure if I understand this weight sharing correctly.
The what?
The weight sharing.
The weight sharing, yeah, okay.
So if I understand correctly, you slide this window one feature map over your image, and then the weights basically is the same for the slider window wherever it is in the image.
Per feature map.
Yeah.
Yeah.
And then you use different weights for different features.
Yes, exactly. So this is not shared. Think about it more as a kind of signal. I think that's the most best to understand when you think just a heartbeat going through. And is there something, is there nothing? So if you do this again and again, that's what deep learning algorithms in the end do. This W times X that we discussed also last time. W times X is, of course, X is always the first layer, then you have to have the output of the previous layer. It's just a signal going through and strengthening or weakening. And when you find a feature somewhere here and say there's some interesting property, you can just share that across a space and say, okay, in that case, constellation of the spatial property, we are in the space of 5 by 5. When this signal, again, is the ear here, is not so important for me. I just learn how an ear look like. And when the signal, the same weight strength comes again on the top of it, it's the same thing. Right? And with this, you're even partly in the way that even if an ear is like slightly, in different areas, or the eyes are in different areas, you get this location, kind of, you detect these across the entire image. But, and this is not the but, only per feature. Right? So in a sense, we reduce significantly from the dense connected to one feature map. But as we created more and more feature maps of capturing different features, we of course extend the number of weights again. Right? I think that answers your question? Yeah, okay. And this is of course just one step. right, that we do in the development of convolutions, of these convolutional neural networks. That's a key essence why they are also so well protected against overfitting. A bit more tomorrow morning about that. Right? Think about this. Weights is really a key problem of memorizing, learning them too much, and having too much weights. With this, we cut weight significantly, concentrate, but also this location independence that we see also they're working with images which are not fully visible, right? And still having a good accuracy just because they have a kind of more location, spatial property really they take into account with this kind of 5x5 local receptor field. This is something very interesting. Right, admittedly here and there it's a bit abstract. Of course, that's why we put it in the remote sensing use case later for you and also in the MNIST use case, right? So that you get some practical experience for it. Then if you think about again, deep learning, lots of deep layers, alarm bells, right? Lots of weights. So how we should continue. There is here a concept of saying when we have now all these feature maps and kind of this hidden neurons, so perhaps this kind of spatial property is important to create the feature, but we don't need it in this fine granularity. We're just interested if in this area we'll do some firing of a neuron happening. And that's all what it is. Think about each of these dots is now a neuron firing, right? The signal again. You can pool out of them. For instance, max pooling just takes the strongest signal from these four, and you do the same thing again over the whole feature map. In other words, what could that be when you think you're a typical machine learning or data mining guy?
Average.
Sorry?
Average.
What was that?
Instead of max, an average.
Yeah, average, okay, yeah. I mean more the kind of sampling approach. When you think about you have lots of data samples, what should that be? And you can come to this, you think a little bit downsampling. Right? So people that now would basically think about, you know, taking bits of the database, you're downsampling to the really strongest signal in a sense, right? And get rid of all the other noise in a sense, right? So this is a little bit similar to that. And with this, again, when you now think about it, here would be a fully connected layer, like the hidden one. How many weights would that be to learn? Right? Fully connected. Every neuron is another one. However, here it's also, of course, connected, but always takes just one signal out of it. Right? So we again reduce the number of neurons. So downsampling. And this is a process we now repeat. Right? We have convolutions taking feature maps. Feature maps are perhaps very nice, very detailed, but we don't need them so much in detail, in a sense, pooling down, sampling down. So this is, in a sense, if you want, the convolutional idea wrapped into different types of layers. And of course, still what remains are the activation functions, right, that we will talk about. So let's come back maybe to the initial slide, because now we know how that is being constructed, right? I say, okay, this is my input. I have weight sharing across the different features. That reduces already my number of neurons. Here I get a feature map detecting different features, like for instance RGB in my image, right? Typical idea of doing this. Then basically you come down to this sampling or pooling, and there are different poolings, so average and as we just discussed here, or the question was alluding to, but max pooling is mostly the one used because it's about the strongest of the signal, right? You must be mostly interested in the end of the network of saying the strongest signal for this indicator of all features will survive, right? And this is a key property of this convolutional network, still fighting overfitting inherently, in a sense, as a part of regularization. I will come back to this tomorrow morning, because in a sense you can see that now already as a kind of inherent regularization approach. Less weights. You know, neural networks, we will make the case tomorrow, they have weight drop. You drop completely weights and you have better accuracy just by weight drop, right? This is something I allude to tomorrow and we'll talk about. Anyway, so let's continue with the basic properties of convolutional neural networks. I think the rest you could already nearly imagine what will come, because you know that already. So when we have now the signal, we said in the end, actually we just need 10 probability signals of saying the strongest signal would be the indicator of saying it's an 8, it's a 7, And here we just use what we used before, the kind of dense layer which gets all this information together and basically then makes a soft max around it. So squeeze everything, if you remember, between 0 and 1, the signal. And there where basically the property is here in the probability the highest, will fire and say it's an 8. Right? That's how we determine that's an 8, that's a 0, that's a 9. But we have to go through that process. But the interesting, beautiful thing is it works significantly good, and we will try out this now together, also on the Gen CPUs. And you use similar aspects that you've done before, gradient descent algorithms. Basically the weight, this hasn't changed so much, right? We still have weights. And we have an error that we can measure here, because we have supervised settings. We know at the end, this should be not an 8, it should be 9. So this is something I can measure up in the cross entropy or mean squared. Let's put this as the example and propagate the error back still. You have a connectivity here, right? And also it's not recurrent, right? Like in the LSTM we will talk about in lecture 6, which is then a bit more complicated. But you can unroll things and then it would be handleable. So this is an interesting property. And now it's a time also that we think how we can go and do that on our own. For this we need a little bit a different thing now. So changing from a perceptron to hidden neurons, hidden layers with lots of neurons, it was kind of an easy step, as you can see. And a little bit again, we should start at the back, where you think like dense a number of classes, right? So that's something what we had already. This is this part of the part here, where we said this is what we done before. All what we did here some hidden layers. Some general neurons in hidden layers in front. This was our hidden network with 2 hidden layers, having still very good accuracy. And now we will try to beat that even, this good accuracy, just by having a very dedicated property, basically which is this local connectivity that we kind of see modeled here. Right? The key message is it's not just once here connected, right? So we omit here in this displays usually in deep learning all the way. While in neural networks here and there you can do that. It still looks not nice as you have seen in one of the almost overfitted ones. Of course here more connection to the other feature maps. Right? So the visual representation should not fool you that there's just one weight connectivity here. So all of them are connected to the feature maps. However, as we do it, is basically as you see the same structure twice, for instance. That's a specific construction I prepared for you, just as an example, because I know we're going to be working. No one told me exactly you have to do it this way always with that data set. And this would be your key problem. When you come now in science, like neuroscience images or remote sensing images, no one tells you how that actually look like. All what you know is you have a convolutional process detecting features. These features you need to downsample, and then you repeat and repeat. Of course, then having more and more convolutional layers depends on your application. Does it make sense? Does it not make sense? How many of the feature maps you have, right? How do you determine that? Also not an easy question in a sense. Here and there you can, as I said, looking on some signal, let's say properties like RGB, that would be kind of, you know already there's a pattern probably to be detected in the RGB of an image. So let's take 3, but if you have more sophisticated spectral channels, you probably consider more features. In general, this is something, of course, also to experiment with, to create. While this output layer here with the softmax and everything is mostly very clear. All you have to do is sometimes, if you use convolution 3D, for instance, you have to flattening here kind of the kind of layer or the input signal really, because you have a typical neuron, right? Connectivity, like you know already, a dense connected layer, so you need a kind of flattened vector. It's another vector we will talk about in remote sensing called flattening. So let's leave that out. This is the construction you have. This is a model that I prepared for you if you want to go and look in parallel now inside your directory. Although we are in the deep learning part, I think we still have to copy first, right? Oh no, we have the MNIST CNN already here. Everybody has a CNN in the home directory, right? The Python. Have a look on that. That's the one I'm going to edit here. Keras MNIST CNN. And you see it's nothing else that I just discussed. Graphically, we create basically convolution 2D. We go in the next lecture sophisticated to 3D. And I will make the point with tensors and multidimensional arrays and so on. Let's stick quickly to 2D. So kernel size 5, that was something what you have seen in terms of the spatial connectivity. We call that also partly a kernel, a learnable kernel. Right? The signal, this 5 by 5, is a learnable entity for this particular feature. So kernel size 5. Padding is something when you reach the end here and there and will not fit to your image sizes. You have to have sometimes a padding of saying some values needs to be added, right? So that it fits to the convolution depending on the kernel sizes and everything. So that's something where you have to consider same or the different properties, how you can put that. In the beginning course here, I think it's just, take this as given. And then the specific input shape you basically get from your model. So this is a general class still, right? I will make the point how it is integrated in the Python script. It's a normal way of creating kind of different classes for different ways how you build them. Because the normal aspect before preparing the data to be going into the network will remain in a sense the same. Also the output is pretty clear, how you model, how you fit. Optimizers are very clear. What you experiment with usually is this kind of setup. So what activation function is better? So today we could say in many cases Riedel worked quite well, interestingly enough, right? But here and there might be problems where more sigmoid or other activation functions play a role. While the softmax at the end is pretty given because we want to give a probability which class, at least in multi-class classification. But this is something to experiment with, especially also when you think now about the pooling. Maybe depending on your signal, it's more important to capture a bigger pool size. This 2 by 2 was just an example. You can have different ones. And this strides essentially saying how we're going through with which offset basically through the data set. Do we do overlaps? Do we don't overlaps? So you see lots of configuration options. If you go to Keras, to the kind of way how convolutional 2Ds are shown in the API, you see it's a rich API with lots of parameters to steer. So that's this little thing here actually is loaded. That's where your most time goes in creating CNNs, because you have to lot of experimenting. There's no perfect recipe of saying it always works well. Of course, nowadays we have some recipes if you want, depending on other very successful neural networks like AlexNet. Who has heard from AlexNet? No one, okay, you see, there's, at least in the deep learning community, a couple are. Then you have Google the Net, who have heard from that, it's also very famous, for instance, just 2 examples, where there is a kind of proven way that it worked well for images, for scene classification at least. That's something where you want to create, and if you a little bit look into the literature, if you want, this is very close to the Google Net that I created here. So there is a way of saying this very much could work well to your data set. And this is of course something which in transfer learning in lecture 5, this will be interesting. So it's a bit too much to put that all again in one lecture, because essentially now we want to know how it works at all. So let's keep that for later lectures, right? There's a kind of recipe still. Experimenting with these kernel sizes and so on is a very important aspect. Indeed, here you see already the flattening aspect that is not really shown on the visible expression, mostly because what you come out here is a kind of 2-dimensional thing, right? That we had also in the kind of MNIST before. What we want to have is a kind of 1-dimensional vector we can put into a neural network, so to speak. That is here in the end. The small neural network doing the softmax, like one long vector. So this is the idea of flattening. It will do that also for us. Then you return a model. So with this we actually created and didn't run anything yet. So this is just how it looks like. So in order to do that, I think the best thing would be if we just execute that now and come back to the more description later, right? Because then it can run already in behind the scene. Again, you have a job script for that. Let me show you that, which is also not very much different. For this, we use the job is CNN sh. So if you look into that, we increased a little bit the wall time here. So just in case, if you experiment a lot, remember if it's crossing 2 hours, your job will run against the wall, right? And depending on how big you do the convolutions and the layers, if you add more and more, it will take more and more time. This is on CPU, so it will take even more time, right? Since the wall time 2 hours. But still, the overall thing remains the same, as you see. Nothing has changed. We have still Keras, we have TensorFlow, as you know. We use this basically just with this kind of new script that we now created. Admittedly, not anymore very directly the same like artificial neural networks. We will talk about it. Please do that now. So submit this script using your reservation, right? Remember, we're using the CPU on Gent. Yeah, so it's QSUB, the reservation term, and then this particular Keras MNIST CNN. And see if I can restore the reservation. Oh. Right, just do this, and instead of hidden, you have the job CNN and fire. Again, with QStat-R, for instance, you can see the differences. Make sure that you're also really on Golet and not in Leuven. Right, very important. Is there someone who needs help in that step of submitting the other CNN? Just raise your hand, right, so that we can see you. Okay? There's no problem, we can wait a minute. It's better to get something out of the practicals. And the slides you can see later, you have the recording later, but the practicals, your reservation will disappear. So using the computing time now is important. No problems. Okay, well, it looks like we're getting more and more HPC experts here. Good, that's how it should be. Right, again, observe maybe while I continue talking a bit the QStat. Look in your artificial neural network that you reduce in terms of weights. Maybe check the amount of parameters and the accuracy. And just, play it around while I'm a bit talking. The CNN will now take some time, so there you can be a bit relaxed. There will be no direct results. So instead of this, I thought maybe spending a little bit of time of describing what's happening in the Python script, right? So when we think about now what we changed, basically, what you've seen before was a definition of a model that is sitting very high up here. So basically before the parameters, it's coming behind the imports of Keras. So it's something I omitted here because I know it remains the same. All we do here and there's new layers are basically imported. So convolution 2D, for instance, is imported as a layer, and an optimizer, for instance, like an atom. So again, what we see here, interestingly enough, is the number of epochs shrink. Right? If you think a bit like artificial neural networks, the number of epochs we use, for instance, for this particular problem. This says by no means that if you have a very large problem, a really sophisticated problem, you should do that. Right? There could be still the need for going up to 100 and more of hundreds, for instance. But putting lots of epochs, I would be also careful doing that. So it's perhaps a good way to start in that for the simple problem that we have here. Basically, all remains the same in terms of Adam. I already told to you the SGD that you basically can take there. And if you remember, Keras has this option even of saying, this is Nester of momentum. Of saying, this is by far the default today, or the Adam. Both are very similar in the idea that you don't have kind of a constant learning rate, right? You don't go in the gradients still, like stochastic gradient descent. But if you remember, we had a kind of fixed learning rate parameter, which is essentially a step size, how quickly you go downhill. It's a parameter we will discuss tomorrow morning in one of the challenges. Just if you think about Adam, adds to this a velocity kind of aspect, so getting momentum in that. But we will talk a little bit about tomorrow. So it's just another optimizer that you use that typically is faster in convergence. That's why you do it, right? And this is an interesting thing. will be other aspects which make faster convergence. So now we are basically not necessarily saying we get lots better accuracy, but we significantly accelerate the process. Right? The neural network with 2 hidden neurons was already 20 minutes on MNIST, or half an hour, and basically a toy problem to do. Right? So if you think now about having much more bigger pixel sizes or another image, you would think of you need much more computing. So reducing the computing now is again one of our goals. And having a better optimizer that in each iteration gets faster to the minimum, that's still what we want to do. We have an objective function like square error, or basically the critical cross entropy we actually use here, just with another optimizer that proved to be better and easier in convergence, right? However, it's an advanced topic, and of course in the moment I would say even here is lots of research to be done, right? To see where does this Adam optimizer fits better, where does SGD plus Nesterov momentum, these are papers, so it really leaves here the tutorial space and goes more to research. Anyway, so essentially what we do here and there stays the same. We have the normalization part. We have a little bit more matrices now, which reflects tensors, and this is something I will talk about basically towards the end of this lecture. Talking about what are these tensors that we shift between, because in the end we are now much more in the matrix space, multidimensional matrix, because sometimes we do things in 2D and even in 3D, as we will see in remote sensing in the other application set that we have. However, we have the same cost, the optimizer we changed, maybe we're still interested in the accuracy to keep our in synchronicity hidden neurons, right? And so if you do model fit, nothing has really changed. Here and there the kind of epochs, we have still a 10 class problem and so forth, and we want to get the accuracy and score on it. So at the end, when you come out, you hopefully should see that we almost get to 100% in that. Right? So that is something very interestingly by having automated this feature learning approach. Questions before I move on maybe and show you some of the applications in practice? Going once? Yeah, okay.
If the images are similar from one to another, can we still apply CNN, because from one layer to another layer we lost some features?
It's actually a technique even that is used if you don't have enough data. So I think the question was if the images are very similar to each other, still can we use convolutional neural networks? And the answer is yes. And actually that is what people are doing for data augmentation. So they use the same images, sometimes 10 times, 12 times. All they do is here and there to basically change pixels. It's exactly good for problems where you don't have enough ground truths, where you don't have enough data. You just create the data yourself. It's a technique called data augmentation. It's usually 1 lecture or 2 in the university. And there are different techniques, but one of it is, for instance, just changing a couple of pictures, or you rotate, right, to detect the feature in a different manner. So the answer is yes. You would do that, especially when you have rare data. Still, it's about signals. Think about that. If you do it 10 times, it strengthens the signal also. Any other question? Going once, twice, shy audience, all convolutions clear. It will be getting more interesting when we go to the 3D, but okay, 2D roughly clear. Good. So let's go to some applications to motivate why we need more convolutions, why we need more layers, and while you compute now on the CPUs, we already want to think about what will be now real application problems. And I just brought you some examples here to show you where that is needed and pointers to where it can be useful. So this is, for instance, a study that we did ourselves. One of my PhD students that did, convolutional neural networks in the brains. I talked about it already a little bit, if you remember. Now, what the interesting takeaway message is, the knowledge you acquire, and I cannot go in all the details, that would be a complete talk, just 1 hour, 2 hours, how we did it. But the key message is the way of learning a little bit how to kind of do the feature maps, how to create the convolutional neural networks. The whole scope basically enabled him to go to a complete different field and actually create with other friends of him a kind of company. right? They still use CNNs, like on the brain data, but now in terms of soccer. So that's why I want to bring this example. So it should encourage you also as students, think about that this really going from research, from interesting new things can really trigger new developments. And they just got from Adesso a 1.5 million grant for, you know, bringing this really into production to the scene. So what it is about, you already see a little bit here alluded, it's a deep, deep network. So what they do is something like looking soccer watches, but before I go into that, let us just quickly see what we learned applied to neurosciences, right? So the idea that we had here was a supervised deep learning. And a couple of you know that already a little bit from last week. We had this data set as well. There are different kind of regions here to be detected, and one way of doing this here is, for instance, gray-white matter segmentation techniques. And what you basically can learn with this deep learning would be then kind of detecting border features. So you realize when these regions are changing, right? Which is an interesting thing for neuroscientists to do. Like here, for instance, Boltzmann area 18 and 17. Everybody sees a difference? Probably not. That's where, you know, human judgment maybe come to the end. Hence, convolutional neural networks to the rescue. Right? And combined, of course, with some other, let's say, elements in neuroscience, it's particularly difficult. But hence, of course, it is nice that there are new models now around. But the idea how that works now is the same thing that you learned. You go with the convolutions over basically this feature space, or basically your images. You detect different kind of features. And here you see you take one by one, as we discussed in the other part. And then you can come to the idea that after all this pooling, after all the convolutions before and feature maps, you're able to detect, at least in certain areas, this kind of different cortical regions. Just based on a property that you can rarely judge as a human, right, for instance. So this is a nice impact factor by doing so. And the neural net that you see is rather... here you have a fully connected FCL, stands for this, the same as dense, right? So think about this, dense, fully connected. You have a convolutional, then the pooling down, another convolutional, and again. So always this kind of repeats. Here and there you would change the kind of activation function. So now how you can apply that in neurosciences, and then suddenly in soccer watch, it's now the recipe that in a way will be with you. So with the same idea how you create in neuroscience an image detection, you can now apply to different fields of different areas. And here is a particularly interesting one, because they kind of recorded soccer watches with one camera. Right? So you have just one camera having the whole soccer watch recorded. And from that, they learned and learned and learned basically how the players and how the fields and how the setup is of these pictures. And this is now the interesting thing. Think about it not necessarily in terms of the soccer players only. We have also information in the soccer field, and we segment this, and we could consider this as kind of different features along the way, right? So what's happening, and an indicator for us what's happening, right? So if you think about, for instance, now there's a kind of camera position probably here, it means that lots of players are in the field, but it's also a kind of feature that here is no one in the field, right? And these kind of aspects you combine. Nothing else. You see here, of course, the neural network for that, which is this one, is a little bit more elaborate, right? And again, probably that would be meaning also talking 1 hour more, and it would have advanced concept we talk about tomorrow with batch normalization. But it should carry the essence that here, when you do that, you have different convolutions, you merge. Different convolutions merge. Max pooling. So the same layers I already told you, in a sense, are there. There are now some boosters, because you see, this is of course not anywhere near the MNIST example. Right? You have now image after image in a time series, changes. And this is quite nice. In terms of what's coming out, because in the end, what you actually want is just x and y of the center of the zoom, right? The goal is, of course, having something like an automated soccer watch, right? And this is a kind of business domain, mostly because the kind of cameraman costs the most in soccer watches to record, right? Today a camera which is very relatively high resolution to put there is relatively cheap. What costs is a camera guy that is always tracking the game all the time, 90 minutes, right? And this is of course something where the business idea of this company comes from. And you see a little bit on the training and test here, it's almost working perfect, right? And it's, of course, admittedly has some interesting 1% where it doesn't work, yeah? The Diego Maradona shot into the air, which just happens very rarely, where the ball is suddenly going nowhere or something. These kind of detections, or suddenly, the keeper would do a goal, very rare connections, where the zoom then not can take place, right? Because they're very rare in the learning data. However, they continue that learning. More and more the database grows, the experience grows. And with this, perhaps also new features will be detected and so forth. So you see, in the end, what all of this magic does with the input convolution, pooling, downsampling, flatten here, right, in order to get one long vector input for the, let's say, last softmax neural network that we already know. And all we need is x, y, and perhaps a level of zoom, how much I should zoom in. So that's an example, and actually you can look at yourself if you want. There, of course, information. And they reduced a little bit the number of information because now there's really millions in the game on that, so they stopped of being too much open about this. Hence, still I got something from my PhD student. The drawback as a professor is he stopped his PhD, so he's out in the business, maybe buying his Porsche, and maybe not coming back. The benefit is we can look a little bit inside what they're doing, and you see a little bit the raw image, and this is really what you learn from the convolutions. There are some tools that you can look into the layers and see a little bit what's happening. So they see the segmented field here and there. It's hard to say and hard to see in this, but you basically segmented the players automatically from the audience as well. So with this kind of learned convolution features, you kind of basically do this on the new kind of playing, right? The new kind of images that now come in from the camera, they don't learn from that. It's a new unseen data and it generalizes well, right? So they zoom quite good, and it's really something where, for instance, they got now 1.5 million as a grant. And of course, now RTL, I think the kind of ticker was interested, or as far as I remember, there were many people interested. They won also this Exist grant. It's another grant for supporting startups. However, the key message remains, if you gather expertise in CNNs for some certain field, it's very easy also, not perfectly easy, but it's very easy to make the move to other data sets, because you learned already how the convolutions work, how the feature maps work, and so on. And this is, of course, a very interesting topic maybe to be in the next years, really. One example I want to show you where convolutional neural networks are particularly effective is autonomous driving. And I was just last week on the Supercomputing conference where you have seen lots of these examples. This is just one of it. And probably also our future we all face.
Maximum speed 50. Maximum speed 70.
Does someone recognize the city, by the way? No, neither me.
Maximum speed 100.
So the autonomous driving has its limits, right? Of course, much harder to learn for network.
Maximum speed 30.
Different lights, shapes.
Maximum speed 50. Maximum speed 60. Maximum speed 70.
All right, so I think you get the essence, right? So we can stop here. That's probably our future. We can do our emails and then the car will take the driving. Right, okay, I mean, there's ethical discussions around that and there are questions of how much we can trust. Just a short side remark from a conference I attended just recently. It's a supercomputing conference in Denver. NVIDIA had a presentation and we were discussing how far we go of saying not convolutional neural networks create other convolutional neural networks, right? Why not should the network create the network? It's much better than humans in learning that, right? So then where the ethical discussion starts, and at the same time there was even Boston Dynamics having this new robot. Has someone seen the Boston Dynamics robot with a salto? No, the first time, like human, right? And when you combine these two and see, you know, this was trained by deep learning, the other one was trained by deep learning, you come to a network that trains itself, that reproduces itself, can create factories, creating robots, you probably know where the end story is going to, right? So it's not far that we are at this capability in the sense. Of course, NVIDIA had there lots of discussions and lots of examples of autonomous driving, where GPUs are used, of course, for supporting this in the future. But we are not yet still at this step of saying the neural networks creating the neural networks. And but of course, this is one of the next steps where you think about where we're supposed to spend time on. Right, where I said earlier, feature engineering was there in the past. Now we spend on CNN engineering, right? We kind of work out how the best layers work together. So if that can be automized, that would be also a major step for us. However, then it's more an ethical philosophy of saying also when is the point where the machines don't need us anymore, right? They just go ahead and do what they want and so on. I leave it at this in the moment. Looking a little bit more on the tools, and yeah, there's a question. Yeah, please, go ahead.
How far do you think we are from that point?
It's a difficult question, especially in a recording. No, there were discussions in supercomputing around that, and around that I can say there are lots of regulatory aspects, lots of ethics communities that have a sharp eye on this, right? Of saying, you know, the way of combining that with robots, everything automatic, that the machines doesn't need us anymore. Autonomous driving is there. It's just waiting for law to follow, right? So the technical capability is there. We have seen many examples, and supercomputing was a small car, autonomous driving. That's not the key issue. I think now the regulatory aspect in terms of law, what happens if, you know, machine learning, we have seen the science, 99%. What happens if the 1% determines a human life? Right? Is it a stop? Is it not a stop? Should I stop? And then these kind of things are not in law yet, and with that it's getting very difficult to deploy that on roads. Where I think, you know, I think in US states it's already here and there tested. In Europe it will probably take a longer time. So I cannot give you a really precise years number, but I would say maybe US 5 years and Europe 10 to 15, where this is regular for here and there common practice. Maybe even earlier, but typically from my experience lawyers will take a long time. And lawsuits that develop the law. It's not that they will now ship her off and, you know, will tackle all of the law cases that will happen. Law works differently. They just create cases for incidents that happen and strengthen the law in this incident. They have no time to do law for everything. Complete regulatory framework or something. That will take a long time. Hence, technically we're there, but from the practice of allowing now BMW doing this completely automatic, I mean, here and there are lots of assistants. Also, if you look at Mercedes today, how they do that, it's already lots of assistant systems, but completely autonomous driving everywhere. I think that will take some time still. Okay, another question maybe. Going once? Twice? Okay, towards the end of, yeah, okay.
One question. Is there any other field, other than, let's say, image or visual recognition, that the convolutional neural network is also because I see that maybe it's mostly used on image or visual.
Yeah, I would also say the question was if there's another field using convolutions. You could say here and there in signal processing using convolution, and the idea that the spatial signal digestion, so to speak, help of having the time step before. But then we just quickly go into the LSTM domain, long short-term memory, which are perfectly for time series. So I think it's a gray zone, but I think 90% are object pattern recognition, vision activities, not necessarily image-based, also video-based, as we see in Soccer Watch, essentially is a time series of images where they're very good. In the end, also the CNN in particular needs to take away spatial property, right? And this is, of course, a big win in these convolutions and poolings. Okay, if there are not more questions toward the end of the lecture now, let's look a little bit at the tool sets around, right? And this will be not to the degree as it is, perhaps from low-level technical, just for giving you an overview what you could maybe study or where you can look what tools are existing. So the one differentiation we have clearly is HPC, where you have, GPUs and cores that are usually very good interconnected, where you use kind of things where there's a CUDA kernel you can deploy on GPU somewhere, or you use Theano somehow with good memory inside. And there's another domain called here rather high throughput computing in a field where you would use Apache Mahout, right? It's based on Apache Hadoop. People know Apache Hadoop, maybe a little bit. It's a processing engine, and Apache Mahout is a machine learning framework that worked with Hadoop. And then on top of this, there's now Apache Spark. Who has contact with Spark before? It's more new, okay? There's MLIT, the machine learning library here, also relatively new. But you can also consider them a little bit different, on a different level. Rather playing in this domain, very much distributed, not a good interconnectivity between cores, while many frameworks are more optimized to this homogeneous set, right? Hence also the difference. So TensorFlow can really work basically with both in a sense, while Theano is really sticking to a more local, and the same also actually with Caffe and Torch as well. So the selling point of TensorFlow in a way from the beginning was always we can do it big, bold at Google and kind of parallel everywhere. However, of course, compilation and so on proves you wrong sometimes, and you see that here and there bringing those like TensorFlow or Theano and Torch into practice could take some while. And the reason is also because it depends on the devices. So as I said earlier, this is a crucial thing. For instance, a version of this, it's kind of the CUDA implementation very effectively, how you basically do your neural networks and so on. And partly these things are basically based on that, the different learning frameworks that here, like TensorFlow and so on, that under the shelf then take advantage of that. It's much better than creating your own CUDA. The people at NVIDIA provide this already as a library. Hence, if you have an old library from that, it could mean a hell of a lot of difference already between that. But this is really getting low level technically on the API calls, what you can use and so forth. Then other aspects are scikit-learn, which are much more Python oriented. It's like someone knows scikit-learn. Okay, that's, for instance, an interesting package to study. Not so much for parallelization, it's also serial on Python, but has some packages to extend. And of course R. And I think the others are not so much important. I think I covered the most significantly. While you basically see that Theano, Caffe, TensorFlow, Torch, this is a place to be. And Keras maybe on a complete different level, right? As we know, Keras doesn't compete with them. They are kind of on top of Theano or TensorFlow. But these are the kind of frameworks that are around, and they're growing. CNTK, Microsoft has a new one. Perhaps I should mention this one, a Java deep learning framework, right? It's also interesting for the space of Java, deep learning for J. So this is all, let's say, the different kind of deep learning packages you're faced with. And then it depends what machine do you have, or which kind of infrastructure you have to accelerate your processes. Right, and we will now see from lecture 2 to lecture 3 and overnight that using GPUs for complex problems, for instance, will significantly increase the speed. right? But of course, you need to have those GPUs in place. If you don't have it, then you maybe can also use those. It will just take longer, but at least you can do the job, right? It's an important consideration just for the tool sets. So when you look on the frameworks, I already discussed TensorFlow, open source, supports CPU and GPUs. We train on the GPU and then deploy on commodity clusters here and there. Something we also have to think about, right? When you think about coming back to this, so the optimization and so on, doing very powerful, costly cluster, lots of interactions, the weights, they have to interact with the matrix multiplication in the end to form the next set of weights. So there are lots of optimizations that take place to get the error change propagated to everyone. So all of this needs a bit communication, good for our full course. But once this model is trained, right, we have a model where we just put a signal in. And this is very, very nicely, firstly, parallelizable, so it has no necessary anything connected with the other signal we're sending through. Secondly, we can say this can be nicely parallelized in a different manner. We don't need the powerful. That's what we mean with commodity cluster, and here optimized per GPU on a cluster. So this is also a scene we see when you come to the kind of real how it's working. They don't train again and again the network all the time. You do sometimes stop off your data, you train the data on it, deploy it, then use the model for a month, and then come back and retrain on new data maybe to make a better model. But of course this is something which also then costs in terms of computing time. Hence this is also an interesting aspect here, which is sometimes interesting of the capabilities of the models. Also TensorFlow is the same thing. You can basically use GPUs and CPUs. You train on the GPUs, and once this is trained, the model you use. And what is the model actually in deep learning? We didn't discuss it so much. In support vector machines last week, we looked at support vectors. In a rent, what's the model? The layers and? Well, exactly. So what you end up with is a big set of weights between all of the different layers, right? So in this sense, once you have this, right, then you basically use it just with the CPU, send the signal through and classify your new unseen data. Theano is then another one, also transparent, very much based actually with NumPy, an extension of this. Also an interesting library. In general, it is like, I think here is the most easiest one perhaps to understand, and the most capable one in terms of computing broadly. However, they have definitively also capabilities in terms of how you program, deep learning models, and also they are very much in some of the benchmark quicker than TensorFlow because they don't have the distributed capability. They can do some things better, but it's also vanishing with more and more being basically depending on the CUDA library and all of these things. So it's a hard thing to benchmark anyway because you tend to switch clusters, you switch GPU versions so quickly. K20, K40, we will see here in our example, will already make a major difference. Anyway, so what is a tensor perhaps at the end? TensorFlow, you should know what a tensor is. There's actually absolutely no magic inside that. I love this very much. Basically, it's just a generalization of a typical one-dimensional tensor. It's a vector of dimension, and then you have a two-dimensional tensor. That is a matrix, right? And then the multidimensional the multidimensional array that you have here, that is basically then what most people refer to as a tensor in the moment. But you can see also that these are tensors, and then you go 4-dimensional, 5-dimensional. This will now be a motivator for the next lecture again, when we break a little bit, and we'll think about what could we do if you think about 3-dimensional convolutions and things like that. So we discussed a little bit 2-dimensional convolutions. Let's go a bit more sophisticated, multidimensional. That's what the frameworks all support, right? And this is, of course, an interesting aspect to study. What we didn't cover was this chain rule. Let's have just 2 minutes about that and see with that automatically how TensorFlow works. So interesting enough, TensorFlow is our backend. All the time you working with Keras, you automatically use TensorFlow. And basically what it creates from the dense, from the model add flatten, from the model add optimizer activation, all of that ends up in a graph from TensorFlow. Right, and here kind of simple notes on the left. Let's start with this first, because in a sense TensorFlow is nothing else as a graph engine underneath. So you would have a typical addition here, z, x plus y, would end up in some representing the variables, and then some node representing the operation. Right? So this is of course something where it goes to the result of the operation, and the edges here will do some interesting thing with it. So this is a very simple example. The dot product we had, for instance, last week, x transpose w, then plus the y's would be, in a sense, modeled like this by TensorFlow. So we would again have the variables, the edges represent something to do, and we know dot-wise, product. And this is, of course, something we're interested in that manner to get this transpose xw. Then we have this kind of intermediate results, and we have an operation here doing the plus b, and go on. So interestingly enough, when you think about how a neural network is creating kind of its function, in the end we said we had basically the simple model that we do function approximation. But what we really do in neural networks is, because we channel different perceptrons over each other, we stack them. And all of them have non-linearity activation functions. We would say the results of different functions are again a function. Right? And put that in a function. So in a sense it looks like that. You would have a function of some w given into a function as a result x of some g function, and on and on. Right? Everybody can see that. It's like a function of a function of a function of a function, what you do in this networks. However, as we also discussed, how you do then the error. Right? We discussed the derivatives are very important to go to the minimum, and there we left it with this kind of chain rule. And this is now the most theoretical I get, where basically the derivation of this has a very nice property of just creating out of this this interesting multiplication that you see here. And this is kind of the chain rule. That is really why backpropagation works, right? Because you can backpropagate this, which is nicely shown in a sense here, that the error of this one function has to be, of course, recursively going down to the one function you learned before in the previous layer. Right? And with this chain rule, you can propagate the error back then, and over time, basically, then make the changes to the weights. And this is basically how TensorFlow is doing it. Hence, it has this structure of the graph, right? No one told them this one, but this comes, of course, from the kind of optimizer that is now taking place. So TensorFlow adds here and there several nodes, depending on what you're basically kind of doing. But in the end, everything is a nice graph, and then you can do very nice things like optimize a graph. When you have computed already a subgraph, which is very similar to another subgraph, basically identical, it will be kept and not recomputed. So lots of optimizations that here and there are very much known from other fields of computer science take place in TensorFlow, which is quite nice, and why it's also getting better and better. They improve on this very much in the last 5 years. Right, so having covered that, I think that is a little bit really understanding under the hood why TensorFlow works so well, and what's happening then in the GPUs is kind of in these different subgraphs. And now it's time, before we maybe have a summary about that, to check your model if the convolutional neural network is maybe already ready. We have a cold break, so I hope it will be finished then. You can just do qstat minus a. In my case, it's still running, like 36 minutes. Anyone already finished, maybe, by chance? Oh, there's one finished. Wow.
I submitted on my own server at home.
There you go. There you go. You know, and you have a kind of NVIDIA, Kepler, or
GBA,
Pascal. You see, another type of GPU. And of course, much quicker than maybe the ones we have here, or we basically use CPUs here. Remember, so on a GPU, this problem might be much more quicker. How much do you need in terms of computing time?
1.5 minutes.
Here you go. That's the difference between CPU and GPU, right? And admittedly, of course, this is a toy problem, which we have now with MNIST. So also, when you have remote data sets, maybe you can start that already. It will be also taking a little bit more longer. You see here on my example, it's still running 36 minutes, for instance, just doing the optimization, the backpropagation, the things you see in the chain rule, right? Doing derivatives, updating the weights. next iteration with the epochs and batch sizes we discussed and so forth. Right, so let's have a concluding video how that works. For those who very much know how that works with the chain rule, I think in the light of time, let's have a little bit of break, and you can consider this as a kind of background noise. But it's perhaps interesting to understand again the TensorFlow model with the derivations and backpropagations in a more lively sense.
So we're going to start with a simple function with two variables x and y. Now first we're going to look at how you were probably taught to calculate gradients in school. Just as a reminder, gradients are the derivatives of a function with respect to all of its variables, in this case both x and y. So you start, in our case we're going to start with our tree representation of the expression. And we're going to start at the root node, which is multiplication. And if you recall, the rule for differentiation when you're doing multiplications, we take the derivative of the left side times the value of the right side plus the value of the left side times the derivative of the right side. And then we just traverse down our tree. We have dx equals 1 on the left side. On the right side, the rule for addition is we just take the derivative of the terms and add them. And we calculate those values and then substitute all this into the expression at the top, and this gives us y plus x plus a. The problem is we now have to go back and figure out what the derivative is with respect to y. We only calculated the derivative with respect to x, and so this can be really time consuming, especially if there are a lot of variables in our function or if it's a complicated function. So this is the naive method. With backpropagation, what we do is we calculate the derivatives for all of the variables in one fell swoop. So we're going to start with an error value that we initialize to 1. The output of this function with a matrix, it would be a matrix full of 1s. And the rule for multiplication is we're going to, for the left-hand side, multiply the error by the right-hand side. And for the right-hand side, we're going to multiply the error times the left-hand side. This rule might seem kind of arbitrary, but if you think about it, it's actually closely linked with the rules that we used on the previous slides. And for addition, what we do is we just send the same error down both branches of our tree. And to calculate the gradients for all of the variables, so for x, what we're going to do is we're going to add up the error at each of the x nodes. So we've got y plus x on the left x node, and 1 times x on the right x node. And then for y, we just have 1 node, and that's going to have the derivative of x. There's one other optimization that backpropagation uses. We calculate the output of each node in a single forward pass and cache it at each node, save that value of each node, so that values like y plus x don't need to be recomputed during the backward pass. So to illustrate the amazing power of backpropagation, we're going to have a 4-way race. We're going to need a pretty hefty function to demonstrate the difference in performance. So I'll be using the LSTM that I built on a randomly generated data set. In my previous presentation, I demoed the ability of my program to optimize functions with a single tuple parameter. This time I'll be using a function with 13 tuple parameters, each containing 20 by 20 matrices. So performance is going to really be critical for this. So our contestants from left to right are, on the far left, in lane 1, we have GPUs and backpropagation. In lane 2, we have backpropagation of in lane 3, we have the CPU using the naive optimization that I showed you earlier here. And finally, in lane 4, we have the naive version of the GPU. So let me just ask, are the contestants ready?
Yes, yes, yes. Yes.
All right. In that case, on your marks, get set, go. See that the LSTM on CPU is optimally, but oh my goodness, the GPU overtakes it. And lanes 3 and 4.
GPU backprop.
Things are really silly. So that, ladies and gentlemen, is the amazing power of backpropagation. And Thank you.
All right, a bit drama to the break. We break here until 10 to 3 and come back. Thank you.